This lesson is about polyprotic titrations and acid-base indicators. I'm assuming coming into this lesson that you've already learned how to obtain the pH for a pure weak polyprotic acid, as well as the pure intermediate forms, pure polyprotic weak base, and buffers that are made from polyprotic acids and bases. The first step in a titration is to figure out what the reactions are. Here we have a plot where you've got volume and pH. We can see that we're starting with an acid because we have a pH less than 7 at the beginning, and the pH is increasing throughout the reaction. The plot is labeled as adding sodium hydroxide to carbonic acid, meaning that sodium hydroxide is the titrant in the burette dripping into the flask, and carbonic acid, or H2CO3, is located in the sample flask. The first reaction then of this titration, because it's polyprotic, we will have multiple reactions, is the carbonic acid with the hydroxide ion from sodium hydroxide. That produces bicarbonate and water. The second reaction is that the bicarbonate will react with more hydroxide ion from NaOH to form the fully basic version, which is CO3 or carbonate. One of the important things that you should recognize about titrations is that you always need to have a strong reaction. It needs to be a complete reaction. Sodium hydroxide is a strong base, and because of that complete reaction, we have a one-direction arrow. So these are forward arrows towards the products. They're not equilibrium arrows. Regarding the equivalence points, when we have these two reactions, the equivalence point means that that reaction has come to completion. So our first equivalence point is when H2CO3 is fully converted to HCO3-, and that is our first steepest point in our plot. So right here, that was supposed to be a drawing, right here, first equivalence point is going to be that location. Our second equivalence point, which is up here, where I'm drawing red, is going to be when the bicarbonate is fully converted to carbonate. In that location, it is our second steepest point, but you'll notice that the steepness of this has to do with how strong the acid character is. So you have a very steep transition here and a more mild slope there. In between the starting point and the first equivalence point, there is a buffer. And that buffer region is marked above this plot where we have the identities of our different components, with H2A starting out at the very beginning. And then we go through this buffer zone as you head towards the first equivalence point. The fact that we have H2CO3 being converted into HCO3- means that both of that polyprotic acid and base conjugate pair are present, and thus you have a buffer. You can really see the buffering in effect through here because of the flatness of the curve, where we don't have the pH changing very much due to that buffering effect. So when you examine a titration chart like this, it's important that you don't mistake equivalence point, which is the steepest point, for halfway to the equivalence point, which is our area where we have the best buffering and pH is equal to pKa. Within this entire buffer region, between V0 and V equivalence point 1, V being volume, the pH is going to be described by the Henderson-Hasselbalch buffer equation, where we're using pKa1. In between the first equivalence point and the second equivalence point, now in this region, we are going to have a second buffer, but this buffer is describing the equilibrium between A2- and HA. The pH there is going to be determined again through the Henderson-Hasselbalch equation for buffers, but this time using pKa2 and A2- over HA-. We finally have this excess region, which is after the last equivalence point. In that region, the pH is going to be determined by the excess amount of titrant that is added after you've completed the reaction. The titrant is usually the strong part of the acid-base reaction, and so it dominates the pH effects. For example, in this case, our extra strong sodium hydroxide that we add is going to be much more of a big contribution to pH compared to the weak A2- that was generated from the titration reactions themselves. To review, for our polyprotic weak acid and strong base, on the right-hand side, there is now a more generalized plot of pH versus volume of base. You'll notice there are unique points A through E, as well as regions F, G, and H. At the beginning of this titration, we have added no base whatsoever, and so we have the pure weak acid in water. Therefore, your approach to finding pH would be to find the pH of a pure weak acid, such as H2A. At point B, this is 1/2 of the way to the equivalence point. This is where we have that special case of the buffer, where the pH is equal to pKa1 because we have equal concentrations of H2A and HA-. At point C, this is our first steepest location, this is equivalence point 1. Now you've completely converted H2A to HA. The pH will therefore be found using their equations for a pure intermediate of the acid. Halfway to the next equivalence point is our second buffer location. So there's a region of buffer, but there is this halfway location where pH equals pKa2. And our second steepest point, E, is the second equivalence point, where we've now fully converted HA to A2-, and we'll find the pH using the formulas for a pure weak base, understanding, of course, that it's been diluted. In zone F, we have our first buffer zone where pH equals pKa1 plus log of the basic form, which in this case is the intermediate HA-, divided by the fully acidic form. In the G region, which is our second buffer zone, we still have a buffer, right? But now we're talking about pKa2 and A2- and HA as the acid-base pair. Finally, then we have the excess zone, which is after that last equivalence point, where we're finding the pH from the excess base added. Using this type of logic, you could also figure out the reverse curve, where you have a weak base being titrated with a strong acid. Now I'd like to transition over to methods for finding the endpoint. The endpoint is the measured location of the equivalence point, which is when the reaction has gone to completion. Ideally, you get the equivalence point and the endpoint to be perfectly matched up with each other. Since we're talking about acid-base titrations, using pH meters is one way to measure them. Remember that a pH meter uses an ion-selective electrode that is selective for the H+ ion. And this is a type of potentiometry. I have other videos teaching you about potentiometry. When the pH in solution changes a lot, as it does when we're approaching the equivalence point, the pH electrode takes a couple of minutes to stabilize, and that's so that you can get exchange between the ions in the pH-sensitive glass and the ions in solution. This means that after you drip a certain amount of titrant out of the burette, you need to wait for the pH meter reading to stabilize. As a result, this can make titrations slower, particularly in that area near the equivalence point. However, because this is a type of electronic reading, we do get a voltage out of the pH meter. This makes us able to automate titrations, and there are devices called auto titrators that will titrate for you, which are used quite a lot in industrial labs. When you have a plot of pH versus volume of base or acid added, in this case it's base, you're going to find the equivalence point using the raw data here as those two locations for this diprotic situation here, where you have the steepest slope. However, that location can be a little bit tough to find, and so you can take a derivative, the first derivative, which is the change in pH versus the volume, and the maximum locations here and here on your first derivative plot, those correspond to the steepest locations in the raw data. It's easier to identify the equivalence point if you have readings very often versus if your readings are spaced out. The second option then is the second derivative, which is the change in the first derivative versus volume. You'll read these by the locations where the data crosses 0, and it's really helpful to zoom in. So if we zoom in on this one right here, for example, you're going to connect to your data with smooth lines, zoom into the point where you can really see the volume, and then you can read the volume off the chart. I want you to notice also that this is a micro titration that this example data is from. Only 88, 89 microliters of sodium hydroxide were needed for this small scale titration. Another alternative for processing the data from a pH meter is something called the Gran Plot. The Gran Plot is an alternative to using derivatives. As I said, the titration data near the endpoint where the pH electrode is really slow and there's not a lot of buffering going on, is going to make the data less accurate near the endpoint. And of course, that's sad because we care about the endpoint. Our derivative approach for the derivatives of the pH becomes problematic because we are taking derivative near where our data is the worst. So for less error, we can use the data leading up to the endpoint, so before the endpoint, to extrapolate out what the equivalence volume would be. This is called a Gran Plot, and it appears like so, where you have the original volume of base on the x-axis, and then the y-axis is the volume of base times 10 to the minus pH. That volume of base times 10 to the minus pH here is coming from a derivation from Gran, which includes the various activities of HA and of the A minus, for example, along with the equilibrium constant Ka and the various differences in the volumes, okay? So you don't really have to remember all of the details about the derivation. I certainly never do remember them, but the concept that we can make this altered plot and extrapolate it. Now we're not using the entire titration data. We are using data from roughly 10 to 20% before the equivalence volume. So our equivalence volume here is about that 88 microliters. And so you can go back maybe 8 microliters or so to 80 microliters, so the 10% prior in this case. The x-intercept, when you fit to this line, and so we have this line going down, that x-intercept is going to be the actual equivalence volume. What you should note, though, is that the data curves right near that equivalence volume. And so you have this information right here, which is not included in the fit. That's the data that's near the equivalence volume that is affected by errors in the pH reading. It's really this earlier data that's coming up about 10% before the equivalence volume. And then I would probably reject even this data point as well as those 3 from the fitting. And then you're able to use this trend line to figure out 88.4 microliters is the equivalence volume in this case. Now, all of that with a pH meter requires that you have a pH meter, that you have the time to use it, and then that you're going to do some data processing in Excel. That can really slow you down. So an alternative to finding the endpoint is to use acid-base indicators. These are compounds whose color depends on pH. They essentially are themselves a weak acid or base. For example, an indicator could be a colored red if it's in the acidic protonated form, and so we'll abbreviate that R as our reactant that's red. And it can be in equilibrium with its basic deprotonated form, which let's just say is yellow, and so is Y for yellow minus. And that equilibrium is going to be described by a buffer equation where we have pH, we have pKa, and then we have the 2 basic and acidic forms of this. The indicator color then is going to change about 1 pH unit around pKa, because that's where you're going to have a ratio of 10 to 1 or 1 to 10 of yellow and red. So you'll be able to tell the colors apart. Many of the indicators that are out there have several pKa values, so they're polyprotic indicators themselves, and will have multiple color changes. An example of a good indicator is thymol blue. It happens to be diprotic. So thymol blue in the fully protonated form here is red, and around 1.7 pH, it transitions to yellow after it's lost 1 proton, and the second pKa of 8.9 goes from yellow to blue. Because you can see here so easily that we do have an acid that would react with a base, I want you to understand that your indicator adds a little bit of acidity to your solution. So whatever analyte you had would be an acid, perhaps. And so you really want to make sure you're only using a few drops of indicator, because if you add too much indicator, you can end up titrating the indicator. It's always wise to do a blank of just the indicator so you can see how much of your titrant it took to change the color of the indicator. Then you subtract that from your titration with your analyte. Choosing an indicator can be something where you're going to look at lists, you're going to try to match up the pKa with the pH at the endpoint. In this example, we have a weak base, starting pH is high, that goes through a buffer region here, and then a steep endpoint. And it turns out that the pH at the endpoint is 5.54. So that's our endpoint or equivalence point, VEQ, equivalence. Of the two options here, bromocresol green has a transition range from blue to yellow, but it's going to be blue at the equivalence point, and it's not going to change over to yellow until you've overshot the equivalence point by a certain amount. However, bromocresol purple has a transition range from purple to yellow that lines up nicely with our equivalence volume. And so the color change matches, in terms of the pKa right here, the pH when you are at the equivalence volume. One last topic is selecting an indicator for a given pH. Here, the question is what a good indicator would be if the equivalence point pH was 4.179. Looking up a common table of indicators, we have the transition ranges as well as the acid and basic form colors. Looking at the transition ranges, we see that methyl orange transitions from red to yellow at a pH of 3.1 to 4.4. Our pH of 4.2 is going to be right where that last red color goes away, and we're getting the yellow color right around 4.4. An alternative would be Congo red, which transitions from 3 to 5. However, our interesting color will be right around the middle of that, and I think it would be tough to tell the difference between violet, violet reddish, and red. And so the color change is not that obvious for Congo red. Looking at ethyl orange, although our pH of 4.2 is right in between the low and high for this, we would try to stop that pH titration at a particular orange color that would be right in the middle. And I think that would also be tough. So in this case, I would recommend using the methyl orange indicator and looking for the yellow endpoint.